One, live.
Good evening, all. Welcome back. For those of you that don't remember, my name is Andrew Farrington. And today, in the next couple of lectures, we're going to be talking about transformer protection. This will look familiar to you. I didn't change anything on my background. The preface of this lecture is transformers. Transformers are extremely important pieces of equipment, and they have specific and unique protection considerations that we protection engineers need to understand and consider as we do our protection designs and relay settings. So we'll be covering how do transformers work, why do we use them, what is it made of, some of the unique electrical characteristics that apply only to transformers, and then we'll get into transformer protection. Differential protection is probably the most important and challenging to understand, I would say. So we'll talk about that in depth. Overcurrent protection, fusing, sudden pressure relaying, and maybe some other protection types, and then other controls and alarms that you may see in your career. I'd like to reemphasize, please ask questions. Reach out to me via email, give me a call. Happy to talk about this or any other topic. So regarding the homework, regarding anything, I guess, reach out. My contact information is available in the slides. How do transformers work? Given that this is a master's level course, I'm assuming everybody really has a general understanding of how transformers work. So we're just going to kind of breeze through this, but I wanted to be thorough and have everything in here in case there was somebody that didn't have all of the same information. So we'll just do a brief review. A transformer is a device that changes AC electric power at one voltage level into AC electric power at another voltage level through the action of a magnetic field. So as current goes through this coil of winding, this coil of winding, winding, this coil of copper, this copper winding, whatever. It introduces a magnetic field, which then goes through this ferromagnetic core, creates a flux, and then that flux thus induces a current in the other winding, and that delivers power to the load. They're usually not directly connected. If they are directly connected, it's called an auto transformer. We're not going to get really into the details of an auto transformer. I could only put so much into the lectures, so we're gonna kind of just touch on those, but we're not going to really focus on other types of transformers that you may run into. Auto transformers, zigzag transformers, three winding transformers. They're all things that you may encounter during your career, but the majority of the work that you're going to do is two winding transformers. The majority of those are going to be delta Y transformers. That's just the way it is. So that's where I try to focus our time. So the only way that these two windings are connected is through that magnetic flux that's in the core, and that provides us with some advantages and disadvantages. The advantages being that they're electrically isolated, so you can have different ground references on each side of the transformer, which is pretty nice. The disadvantages are that you have a separation of of the windings. Sometimes you may want to have like a ground reference on one side or the other, but given your transformer configuration, you don't have that. So they're just things that we can take advantage of, but more importantly, we need to understand the implications of. So some basic equations that govern the ideal single phase transformer are the turns ratio, which, as you all know, is the ratio of turns on the high voltage winding divided by the turns ratio of, or the number of turns on the low voltage winding. This is also the ratio of the voltage on the high voltage winding divided by the voltage on the low voltage winding. And the current is the inverse of the turns ratio. So you have constant power in and constant power out, more or less. In an ideal transformer, that's what it is. And so as the voltage on one side increases, the current on that side decreases by a proportional amount. And because the power in and the power out are equal, we can take advantage of that and do some really cool things. And that's, you know, the primary reason that transformers are used in the power system is to take advantage of this. So because the power delivered to the primary side and the secondary side of the transformer are equal, you know, we can take advantage of some other properties of Ohm's law. And we can see that since power is equal to IV and power is also equal to I squared R, as we increase the voltage in a linear manner, we actually decrease the losses in the system exponentially. And that's really cool. So that's why we have high voltage power systems. That's why we have high voltage transmission lines. That's why we step voltages up, and then at the end of the line, we step them back down, because lower voltages are obviously easier to work with. The distances are the phase distances don't need to be as big. You can use less insulation at lower voltages. It's easier to work with for your power electronics. So we take low voltages in or lower voltages in at generation sites, step them up to reduce losses in an exponential manner, even though we're only increasing the voltage linearly. And then we can step it back down so that the customers can use it. So we can take an example of that. I just came up with this in Paint, so I apologize for the messiness, but I think this will demonstrate the point. If we have an infinite source, say this is our system, and then we had a transmission line with a resistance of 10 ohms, and we had a load that wanted 1 MVA at 1 kV. In this system, we're operated at 1 kV. You can calculate your S base at 1 MVA, the V base at the load of 1 kV, the Z base, which is just the V base squared divided by the S base, which would be 0.01 ohms. And then the current base, the load, is the voltage base divided by the S base, which is 1,000 amps. Excuse me, the other way around, S base divided by the V base, which is 1,000 amps. It would take 1,000 amps to reach your 1 MVA at 1,000 kV. If you have 1,000 amps flowing through the transmission line through a resistance of 10 ohms, you can calculate your line losses, which are the I squared R losses. 1,000 amps squared times 10 ohms is 10 MVA. So you actually have 10 MVA of losses on your transmission line in order to deliver 1 MVA of power to your load. Not real efficient, obviously. That's like, what is that? Less than 10% efficiency. Not real good. But if we introduce transformers into this equation, then now we have a higher voltage base on the transmission line, which I've demonstrated here. At the load, it's still 1 kV, but because these are 1 to 10 kV transformers and 10 to 1 kV transformers, respectively, now the Z base at the line is 1 ohm instead of 0.01 ohms. The I base at the load is still 1,000 amps, but the I base on the line is 100 amps. And in order to deliver 1 MVA of power to the load, you now only require 100 amps of current on the transmission line. And so now your line losses are I squared R, 100 amps squared times 10 ohms is actually 0.1 MVA. So instead of 10 MVA of losses, you have 0.1 MVA losses, 100 kVA. Obviously, that's a lot more efficient. So the takeaway here is that we increased the voltage on the transmission line by 10 times, but we were able to decrease the line losses by 100 times. And so that's the linear increase of voltage, which results in an exponential decrease in line losses. This is why we use transformers. This slide kind of summarizes what we just talked about. When they were both operated at 1 kV, the transmission line losses were 10 MVA to deliver 1 MVA of power to load, which is not very efficient. Increasing from 1 kV to 10 kV decreases the losses from 10 MVA to 100 kVA. So that lowered the transmission line losses by 100 times. There are costs, obviously, with increasing the voltage of the system. You have more expensive equipment. You've got larger phase spacing, which means you need a bigger area in order to put your substation, taller transmission lines, bigger bushings. There's safety considerations with this bigger equipment where you need more space. You can also get higher currents because the voltage is higher, right? So there are safety considerations for personnel if you have a carpool accident or something. You know, there are costs, even if they're not economic costs, they may be societal costs. Clearing bigger right-of-ways, for instance, right through the northern Maine woods. So there are costs, but given that even considering those costs, that exponential decrease in losses can offset those costs, and that's really why Tesla beat Edison in the War of the Currents, which I'm assuming you're all familiar with at this point. But you know, back in the day when electricity was first discovered by Mr. Edison, and he put in a bunch of DC substations, and I think Adam actually had an example of a DC substation in one of his lectures. Those existed, and they were just outcompeted by Tesla's AC current, and transformers are one of the primary reasons why. So utilities, generating facilities, commercial facilities all use transformers to take advantage of the higher voltages. And yeah, this states that, you know, it was decreased at loads for the reasons we already talked about. And please don't go back and try and recalculate what the source voltage would need to be for this, because it's not going to be realistic. I just picked numbers out of a hat to try and demonstrate the point. I wanted a 10 times increase in voltage and 100 times decrease in losses. If you tried to calculate what the sending in voltage in this case it would be far exceeding 1 kV. So don't do that. But the point of the example, I think, is what's important. Yeah, the important takeaway is that we use higher voltages to dramatically reduce line losses, and we use transformers to efficiently change the system voltage. That's why we use transformers. So what is a transformer made of? The tank, which is the body that surrounds the transformer. We've got some pictures on the following slides, so forgive the text. The transformer body is typically made of steel. The core, which we talked about, which is the ferromagnetic core where the flux is circulating, that's typically made of laminated iron that reduces eddy losses. The windings on the primary and secondary side that are wrapped around the core, which we already talked about. Those are typically made out of insulated copper. The bushings are the hollow electrical insulator, and that allows you to basically tap to the top of the bushing, run a conductor through the middle of the bushing, and then connect to the windings on the transformer. So that's what these are, right? So this is your primary conductor, taps to the edge of the bushing. You have a conductor that goes down through the middle, and then that connects to the winding on the transformer. So this is a bushing. If your transformer has transformer CTs, your transformer CTs are usually in the bushings of the transformer. So you'll have a donut CT made of iron that's got some coils around it. You have your primary current that goes down through the middle of the CT, and that is where your CT is stored, housed, whatever you want to call it. The insulation inside the transformer, it's typically filled with mineral oil for our power transformers. The transformer oil is used for its insulation properties, but also for its cooling properties. So inside the transformer, if this was filled with oil and the coil's heating up, you can envision that the oil is going to heat up. You can then cool the oil, which can then in turn cool the transformer. We'll talk about that in a little bit. So it's got multiple properties that are nice, both in the insulation and the protection of the transformer windings and core, and also the cooling properties. The conservator tank, I've seen more and more of these in recent years. I don't know if that's just because my primary client has changed to conservator tank based transformers. Most of them used to be nitrogen blanket filled. We'll talk about that a little bit, but I've seen more and more conservative tank transformers. So this part here is called the conservator tank. So since the transformer is completely filled with oil, when the oil heats up, the oil expands. And so the conservator tank basically is a holding area for the expansion of the oil. And then when it cools back down, it lowers from the conservator tank back down into the tank to make sure that the tank is always filled completely with oil. You don't want air in there. Air can cause corrosion to the transformer windings or the transformer core. That's why it's oil immersed. So the conservator tank makes sure that there's always makes sure that the tank is always completely filled with oil. If you don't have a conservator tank, you'll likely have nitrogen tanks, and they're usually just like a bottle or 3 of nitrogen that keep positive pressure inside the transformer tank. So if you don't have a conservator tank, you can't obviously completely fill this with oil, because then when it heats up and expands, there's nowhere for the oil to go. So you may go right to the top of the transformer with plenty of room between the top of the oil and the transformer windings and transformer core. And then you can inject nitrogen and lay a nitrogen blanket on top of the oil and between the top of the oil and the top of the transformer tank. And this keeps a positive pressure to keep the air out. Nitrogen is not going to react with the iron or copper inside the transformer. So that's better than having air in the transformer. So that's another method. And if you have a transformer that doesn't have a conservator tank, it probably has a nitrogen bottle. The no load tap changer, or also known as the de-energized tap changer, is a way to adjust the turns ratio of the transformer. It's typically plus to minus 5% of the high voltage rating. and it can only be adjusted when the transformer is de-energized, which is why they call it the de-energized or no load tap changer. You may also have a load tap changer. These are very common in power transformers. This is a way to adjust the turns ratio of the transformer, which is typically plus or minus 10% of the low voltage rating, and that can be changed while the transformer is energized. So those are kind of the key pieces of equipment of a power transformer. If your transformer doesn't have an LTC and it's feeding distribution customers, it probably has a series of single phase regulators that regulate the voltage on each phase. So this is an example of a three-phase power transformer. We kind of covered this already. That would be the reservoir or the conservator tank. You have your high voltage bushings. You can't really see the low voltage bushings coming off the back. This is probably, I don't know, Paul, do you know what that is? It looks like a VT stand to me. That kind of looks like maybe a lightning arrestor and then a VT.
Or a combo unit, because I don't know,
Yeah.
like those lower PT, they may be PTs there. It's hard to tell. I'm not sure what the orange things are, because I would have guessed an arrestor like you said, but I don't know what those orange things are.
Yep. This is another diagram. I just found these on
Actually, you know what?
search.
That's on the same side. That might be the neutral connection. So I wonder if that's like a high-speed grounding type device, because it looks like it's on the neutral, correct?
Sure does. Yeah, it's a good point.
So I'm guessing maybe some sort of a high-speed grounding device, just a guess.
Right. Sometimes they'll, like if this is the high voltage side, they'll sometimes put like a lightning arrestor on the neutral if they're not going to ground it directly. So it could be a lightning arrestor. Or, yeah, I don't know. Maybe one's the neutral CT and the other one's a neutral surge arrestor. I'm not sure. The core and the windings are inside here. And then you have, like I talked about, the radiator and fans. If you're going to cool the transformer, usually you'll have 1 or 2 stages depending on the size of the transformer. This is a transformer at Bingham Wind Farm. This is a picture I took. This particular transformer actually had 3 windings. This is the high voltage winding here. And then this is the tertiary windings heading off towards the control building where there's a synchronous condenser connected. These are radiators here. So this is what's circulating the oil, cooling it down. And then you see the fans here, same thing here. These are all radiators and fans for cooling. You may also encounter pad mount transformers, which are used for large customer loads. Typically, you'll see these green cabinets. You've probably seen them, and maybe you did, or maybe you didn't know what they were, but you'll see them all the time now, right? Once you understand what they are, but these are pad mount transformers. So all your connections come in through the bottom of the foundation and go underground. If you've ever wondered what's inside one of them, this is what it looks like. You've got your primary connections. These are your high voltage bushings. This particular one has a pressure relief valve, an oil level gauge, because these are oil filled as well. These don't have a nitrogen bottle. They're not, they're not important enough, I guess, to have the same considerations as a power transformer. These are your low voltage terminals. And so this is one that's kind of connected up. You can see all the low voltage cables. So pretty neat. So yeah, this is what the bottom of the foundation looks like. They pour that foundation with holes, and then you can go down in there and run all the cables. You'll also see distribution transformers, and these serve small customer loads, including your house. You'll see them up on pole tops all over the place. If you've ever wondered kind of what the different parts and pieces are, you've got the primary connections that come in onto the top, and then the secondary connections come off the side, and then they'll go into a conduit, or maybe they'll hit an attachment point and then head across the street to the side of your house, and that's where your feed comes in. So this is the high voltage bushing. This would be an arrestor. These aren't on all roadside distribution cans, but some of them do have it. These are your low voltage connections, and then inside the tank, these are usually oil filled as well. That'll be your coils and your windings. Excuse me, your coils and your core. Another picture. This one looks like it's a phase-to-phase connected distribution transformer. So this is an example of a nameplate for a power transformer, which is what we're primarily going to be focusing on as part of this class. I included this so we can kind of touch on some of the different parts and pieces of the transformer nameplate. You've got your MVA rating. So this would be your ONAN rating. And then this is your ONAF, and then ONAF 1, which is on, what is it? It's open, Paul, help me out. Air fan is AF.
Oil
What's the
natural,
ONAN?
air natural.
Oil natural, air
Oil
natural.
natural,
Okay,
air
then.
forced, and then oil forced,
Okay.
air forced. Yeah.
Yeah,
I'll
that's what I
buy
was gonna
that.
say.
Yeah, they okay. Yeah, they don't have oil forcing, right? It's just air. Yeah, fans. Yep. Okay, that makes sense. Thank you. And then this one, this particular transformer has 2 degree rise ratings. So this 14 is actually at the 65 degree rise. You have your percent impedance. This one didn't have it yet because it hadn't been tested at the time. These are your LTC tap positions. Neutral is here, and then you've got 16 rays, which increases your low voltage winding voltage by 10%. And then you've got 16 lower, which decreases it by 10%. You have the de-energized tap changer positions. So again, this increases or decreases the high voltage winding voltage by plus or minus 5%. This nameplate is showing the winding configuration. So the high side of this transformer is in a delta. It also shows the vector diagram. So this is a DY1 transformer because the high side is a delta, the low side is a Y, and the Y, if you were to like where's my snip? It's probably behind here. If you were going to extend this X1 voltage from over here, you would see that for a counterclockwise rotation, right? If your eye is over here looking this way and you rotated this counterclockwise, you would see H1 first, and then X1 would lag H1 by 30 degrees. We talked about that during the Aspen one-liner lectures. So this would be a DY1 transformer. The other way you can tell that it's a DY1 transformer is that the polarity of the H1 bushing, if we connected this A, B, C, and we had a positive sequence rotation, the polarity of the H1 bushing is connected to the non-polarity of the H2 bushing, which would mean this is a DAB transformer. And we talked about that during the other lectures as well. A DAB transformer is a DY1 transformer. If this had been, you can rewire this, you can rewire the coils in the core, and you can connect the H1 polarity to the H3 bushing, which would be the non-polarity of H3. If you rewired it that way, it would be a DAC transformer, which would equate to a DY11. So these little lines here on the delta winding, these are showing your no load tap changer positions. So if you go back to this, it says like you can connect T5 to T6, and that would be position A, which would give you a primary voltage rating of 38.01 kV. And so that translates down here to your T5 and T6 terminals. So when you change the, and I've got a picture of it, but it's like a bar that you physically move, and it changes these taps to give you your different no load tap changer positions. But that's what the no load tap changer looks like on your nameplate. And then that's what all these lines are. If you ever wondered, why don't they just show a couple coils and tell me what the transformer is? This is why. They're trying to demonstrate all of the different tap positions for, in this case, it's the no load tap changer, which is on the low side, and then, the load tap changer, which is on the low side, and then the no load tap changer, which is on the high side. So that's what all these little taps are showing. You also have some tables here that give you your available CT ratios. I'm pretty sure you guys have all seen this. So, but if you had a CT and you connected X1 to X5, you get the full ratio, and then you can tap it down to get smaller CT ratios. That's what that's showing. This is from that same transformer, kind of showing a picture that is better than what I could get with my camera, something top down, where you have the H1 and H2 and H3 bushings. This is something to keep an eye out for. I'm not sure if you guys covered this in your AC schematics, but all of these transformers, the order of the bushings is always the same. If you put your high voltage winding on top, it's always H1, H2, H3 left to right, and same thing with the X. It's always X0, X1, X2, X3. Same thing with breakers. I'm not sure if they mentioned that too. If you take your breaker and you rotate it to such that you have 1, 3, 5, it'll be 1, 3, 5 on top, and then 2, 4, 6 left to right on bottom. And this is something that does get missed in designs, because a drafter will take a transformer and because it's more convenient to mirror it than it is to like rotate it around, especially with breakers. You'll see it a lot. And that can really screw you up. Seen it happen more than once. So you can't mirror, you have to rotate. And if you're ever unsure and you don't have the vendor drawings, which you should always refer to anyway, but if you don't have them, you can do a quick sanity check and say, okay, well, is it H1, H2, H3 left to right, and X1, X2, X3 left to right when I put the high voltage winding on top? Well, if so, it's probably okay. And same thing for breakers. It should be 1, 3, 5 on top, left to right, and 2, 4, 6 left to right on bottom. This is the conservator tank. You can see it's pretty big. This would be the mech housing. As Paul clarified last time, it's the mechanical housing. So this is where all the bells and whistles, your LTC controls, any other fan controls, any ancillary devices, those are all in the mech housing. You can see this little cutout here. This is where you bring up your conduits to connect to all of the goodies that are in the mechanism housing. This calls it a control box. Yeah, same thing. Off of the X0 bushing, you'll see this kind of, well, it's kind of a rectangle here, but this is a copper bar that comes and bends down and connects to another copper bar, and that ends up going down to a 4-hole terminal pad that you can attach to your ground grid. So that's how you actually ground your neutral winding, your Y windings neutral. That's how you do that. You can see the radiators here with the fans coming off the side. These are the front and back pictures. So your high voltage windings here, low voltage windings here. You can see that they're smaller. Again, the conservator tank, and this is showing that grounding bar comes over here, does a little turn, comes back down, and then this is the ground bar. So that goes down to, I guess this is two holes in this case. And that's where you tie in to your ground grid. This compartment here is the LTC compartment. So this is also oil filled. This is going to control the load tap changer. That'll probably have your drag hands on it. We'll talk about that. I think I have a picture of it right here. Okay, yeah, here we go. So again, a couple more pictures. These are from the side. You got the radiators and the fans. I don't think there's anything new here. This is a no load tap changer. That's what it looks like. So this one's set at 3. So you can see that this is like, I don't know if that's screwed in. I've actually never changed one myself, but you can tell what position it's on, obviously, which is the important thing. So this is the no load tap changer position. You've got to like, you got to really muckle onto the thing to change the position. So don't do this while the transformer is energized. That will be very bad. This is a control cabinet for an older transformer. This is the dial that shows you what LTC position you're on. So this would be neutral here at the top. So this is currently looking like it's probably on 2 rays. And then these little guys right here are called the drag hands. And so it's kind of just like the regular dial, but it's got a little piton on it, such that when the dial that tells you what your actual position is moves beyond this hand, it'll move that hand with it. And then it'll go back and that hand will stay. And so this shows you kind of the range in which this particular transformer is operating. So they'll usually, again, we'll set the no load tap changer position such that the voltage that we want on the low side is around the neutral position of the LTC. Okay. This is for multiple reasons. One, I mean, it's just good practice, right? Why would you want to be operating at between 16 rays and 12 rays, right? That doesn't make any sense. So we want to operate around neutral, but also there are maintenance reasons, and I'm not super familiar with this, I guess, but I've been told that there are maintenance reasons why you want to exercise that that mechanism that changes from rays to lower, and it can prevent malfunctions of the LTC by exercising it. So they try to make it so that the low side is operating around neutral. Looks like they did a pretty good job here. So there's usually a drag hands reset button that would basically just, there's a spring or something that brings those back to the current position, and then you let it go for a while, and then you can come back later and see kind of where it's operating in. This
Andrew,
is the, sure, go ahead.
I'm just curious, what's a situation where you would actually use a load tap changer? Why would you do that?
A load tap changer?
A load tap changer, yeah. Why would you do that?
So as the load increases or decreases, right, it's drawing more current or less current. And the more current you draw through a fixed impedance, you get a voltage drop across that impedance. but you at your house want to have 120 volts. You don't care what the load is on the entire distribution circuit. You want to have 120 volts. You don't want it to be 95, right? So what the LTC does is, as the voltage at the substation bus goes down due to the increased load, it'll tap that voltage up so that at the distribution customers, the voltage is still what they want.
So it's actually automated.
Yes. Yep.
Oh, okay. Okay, thanks.
Yep.
Yeah, if I could just add too. So it's only for the cases where the load varies quite a bit over the course of a day, perhaps. So you tend to see way more load tap changing transformers on distribution circuits because the load varies so much. It would be almost impossible to maintain either the nominal voltage under low load conditions, or low load or high load conditions. So it operates a fair amount, mainly on distribution circuits. I haven't seen a ton of on load tap changing transformers at the transmission level. That's not to say they're not unseen, but they're not as common as they are at the distribution level from what I've seen.
Yeah, like I said, if the power transformer itself doesn't have a load tap changer, likely there are regulators either at the station or out on the distribution circuit somewhere that regulate the voltage for the customers. Sometimes you'll have a long distribution circuit and you can't really, if you have customers tapped along the entire length of that distribution circuit, you can't regulate the voltage here at the station very well and maintain an appropriate voltage for the customers that are near the station and the customers that are a long way away. And so periodically they may install more regulators, 5 miles down the distribution circuit, such that the customers that are beyond that point have an appropriate voltage. There's also something called line drop compensation, where you can, if you're, say your secondary voltage at this convenience outlet here, right, is 120 volts, and that's what you want at people's homes. But you know that you've got a customer that's 10 miles away, you don't really want to regulate the voltage here at the station to 120 volts. You want to regulate the voltage that's at the customer to 120 volts. So the line drop compensation will take the current that is going through the transformer, and you can input the impedance of the distribution circuit, and the LTC controller will calculate what the resulting voltage will be at the customer. And then you can, bump this up to whatever, 125 volts, such that when it gets to the customer, it's 120 volts. So this is all stuff, I run into it all the time, and I'm assuming many of you will too. We set these LTC controllers regularly. Does that answer your question?
Yeah, thanks. I was just a little confused because I didn't realize it was automated, and I was trying to imagine someone out there manually. Why would they do that? You can see the no load one is obviously manual, but now I realize that one's automated. Okay. Yeah, that makes sense now. Thank you.
Yeah, so that's what you have, the no load tap changer. That's, you do that once in a great while, right? Maybe load is shifted over the course of 10 years, and now you need to change the turns ratio of the transformer such that the LTC operates around neutral, or it's a new transformer going into a new substation, and we want to make it so that the LTC operates around neutral. You might change the no load tap, but the load tap can be changed under load, and it's usually regulated by some sort of device that is, so all these dials here are looking at, you're setting what voltage it's trying to use for the band center, and you've got a band width, which, it'll allow the voltage to be anywhere inside that band width. And then if it gets outside that band, it taps it back down and tries to keep that voltage within that band. These may be line drop compensation dials. I'm not really sure. We ended up replacing this LTC controller with a more modern one, but that was what it looked like before. Okay. As I said, the primary focus of this class is going to be protection for three-phase power transformers. Most commonly, these are single three-phase banks. They're more efficient, they're lighter, they're smaller, and they're less expensive. So those are preferred in most applications. Almost all of them have what they call a three-legged core. So this is the core of the transformer, and you've got the high voltage winding and the low voltage winding, and you just vary the number of turns for each in order to change the turns ratio of the transformer. Your transformer may or may not have a fourth leg to allow zero sequence flux to flow. That would be where it would be if you had one. Most of them are just three-legged cores. This is a YY connected three-phase transformer. So you can see that the secondary of each winding is tied together and goes to the HO and the XO bushings. And then the polarity side of each winding heads off and goes to the X1, X2, and X3 bushing respectively. And same thing for the high voltage bushings. These would be in phase with each other. So you've got the high voltage and low voltage windings, and they're in phase, as shown by that vector diagram. And this is kind of showing the, the different bushings and how you're connecting the cores. At very high, like I don't even know where the cutoff would be, I guess, but at very high MVA ratings for your transformer, you may encounter utilities that actually go back to using one transformer per phase, like 700 kV transformers, say. I was actually reading something that there was I think it was 1.2 gigawatt transformer that they were putting in China. And the reason you go back to single phase transformers, there are a couple of reasons. One, you build it and then you have to get it to the site, right? So you can imagine that if you take, three 1.2 gigawatt transformers, or a third of that, 400 MVA transformers, and you got to put them on a train or a barge, and then you got to ship it over the road to get it to a site. Those are big units, so you may get up to a certain size where you can't physically transport the transformer if it's all contained in the same tank. It also provides the advantage of, say you have a three-phase transformer, you can buy 4 of them and you can put them all next to each other. And then if something happens to one of them, you got a spare, and now you don't lose your transformer for an extended period of time. You can switch one out and switch it back, switch the spare back in, and you can keep transmitting power. So that's an advantage for maintenance and system reliability. But in general, most of the applications you guys are going to be working with, we're looking at, 2 winding, 3-phase transformers all in one tank. In 3-phase transformers, we've talked about this before, and I know you guys understand this, but it's really important. The phase angle may shift from one side of the transformer to the other, and that phase shift is defined as the phase angle in degrees between the line to neutral voltage of the reference identified winding, which is usually a high voltage winding, and the line to neutral voltage of the corresponding identified low voltage winding. The angle is positive when the low voltage terminal lags the high voltage winding, and it's negative when it leads. This convention, which we talked about during the Aspen one-liner lectures, is based on a 12-hour clock, where midnight is 0 degrees, and that's usually your high voltage winding. That's why they don't specify it here. So D, the high voltage winding, is at midnight, and this 1 means that the low side lags, because if midnight were here, 1 o'clock would be here, and for a counterclockwise rotation, the delta winding would lead the 1 o'clock winding, the Y winding, by 30 degrees. So 1 o'clock is 30 degrees lagging, 2 o'clock is 60 degrees lagging, etc. You're not going to see a 2 o'clock transformer. I've never seen one. I mean, maybe you will, but you just probably won't. 11 o'clock you may see. Those are DAC transformers like we talked about. And then 12 o'clock would be if you had like a YY or a delta transformer and the high voltage and low voltage windings are in phase. So again, in this vector diagram, DY-N1 indicates that the high voltage winding is configured in a delta, the low voltage winding is configured in a Y, and it has a neutral bushing, that's the N, and that the low voltage winding is at 1 o'clock, meaning it lags the high voltage winding by 30 degrees. And I copied and pasted this from the previous lecture. Remember, it's important to not just look at the vector diagram. You also have to look at the phase to bushing connections and understand the system's phase rotation. Because if you have connections that do not match ABC to H1, H2, H3, or if you have a phase sequence that's ACB versus ABC, this changes. So need to be aware of that. And I really want to emphasize this, if you guys couldn't tell, because this is really important, and it's something that happens, like I said, more often than you'd like to think, right? And I've been involved in at least 4 projects that I can remember off the top of my head where the design was done without considering the phase shift of the transformer. The transformer was put where it needs to go. They built the substation, and then they go to like test the transformer and check for phasing to parallel with the existing transformer, and they find out that it doesn't phase. And that is very embarrassing. You can imagine they want to put the substation in service, everybody's excited, and then you go, oh yeah, this isn't going to work, and now we need to swap primary phasing. It's not good. Actually, Paul, I don't know if you remember, Bristol substation had this problem.
No, I wasn't involved with the startup. I remember doing the settings, so that was Ryan. He took care of that.
Okay. Yeah, I came in as the owner's engineer after it had been built. And yeah, that was Craig Lakin and I went out to the site and had to mark up all the drawings to swap the phases. So it happens. And this is an example from a small municipality where this happened. The site had been built and the municipality had a tie to a local utility at the 34 kV level. So they had a 115 kV transmission line that came into their substation. Then they had 2 transformers in parallel, and then they had a 34 kV system that went out to their local distribution customers. And we got involved in a project to do some work on their system, and we were talking about outage considerations. This T1 transformer was what they were using, and T2 was a spare, but it was unusable, which isn't great. That aside, they had this tie to the local utility, and we were like, okay, well, great, we'll close that tie, and then we can take the transformer out, we can do the work that we need to do, and then we can put the transformer back in, open the tie, and nobody will lose power. And the municipality said, we can't use that tie. We said, what do you mean? Why not? And they said, it doesn't phase. And I said, okay, well, can we rotate the phases or something? And they said, no, it's weird. We hook the phase sticks up to it, and they don't know what's going on. So it wasn't just that 1, 2, 3 didn't line up with 1, 2, 3. It like they couldn't tell what the problem was. And I said, I bet I know what it is. And at this municipality substation, they didn't actually have the primary phasing marked, which is pretty common practice that tells you which phase is 1, 2, and 3, or ABC or whatever. So we walked, Bill Wise and I walked to the substation that was owned by the local utility, and then we walked the right of way because they had the phases marked and we could see it from the road. And we took a picture of what the phases were, and then we walked the substation to see if there were any phase rolls. And then we traced it back to the municipality substation and identified that their 150 to 34 transformer had a different phase connection than the utilities, and that's why they couldn't phase. So we came up with a plan to change the primary phasing in the municipality substation so that they could phase in the future. So this was kind of a sketch that I came up with and Bill worked on me with, and then we came up with a plan to change the phasing on the 115 kV side and then on the 34 kV side. So again, it's important. It happens. It's embarrassing. What's important for you guys is to know how this works, and you can be the guy that figures it out for somebody else and not the person that makes the mistake. You don't want to be the person that makes the mistake. Any questions on that? Okay. How much time do we have? 20 minutes. Y winding configurations. So now we're going to get into the transformers electrical characteristics, which depend on the kind of transformer, right? So in a Y winding configuration, the low voltage ends of all three windings are connected to a common neutral point, which may or may not be grounded. The line current flows directly into the winding. So if you have line current coming in here, goes into the winding, and then it hits the common point or the neutral point. And then regardless of what the other winding is on the low voltage side, say, if there is balanced loading of the transformer, no current is going to flow into the neutral if it's ungrounded. Excuse me, even if it's grounded. If it's imbalanced and it's grounded, then you're going to see that zero sequence current going through the grounded neutral. There are 6 ways that you can configure the Y configured winding. These are those 6 ways, and this is why your clock position has 12 positions, because you can actually change it to something that's other than 30 degrees leading or 30 degrees lagging. But in practice, you don't need to worry about these. You're gonna see Y0 type winding configurations. So, but if you do have a unique application for some reason, you can custom order a transformer potentially with the phase angle shift that you need. Then you have delta windings. Again, you can get other phase shifts if you need them, but almost always they're D1 configuration where there's a 30-degree phase shift. Yeah, this kind of just goes through this. This is important to note. In a D1 configuration here, so actually I take it back. For delta, you can either get D1 or D11. There are 2 common. D1 is far more common, but D11 does exist and is something that you can potentially run into. And if for some reason you're looking at a drawing that doesn't have a vector diagram on it, you can tell whether it's D1, meaning the Y voltage will lag by 30 degrees, or if it's D11, meaning the Y voltage will lead by 30 degrees, based on how the windings are connected. And we talked about that when we looked at this, this nameplate where H1, the polarity of H1 is connected to the non-polarity of H2. That makes it a DAB transformer, and therefore it's got a vector diagram with DY1. That's mimicked here, where you've got the polarity of H1 going to the non-polarity of H2. That's why it's D1. If you have the polarity of H1 going to the non-polarity of H3, That would make it B11. So that would be the opposite phase shift. And again, that would be if you're connecting it ABC and with a positive system phase sequence, if one or the other changes, then it reverses. And if both change, it double reverses. So you gotta kind of go back to the fundamentals, see how it's connected, understand what the phase rotation is, and figure out what your phase shift is going to be. Delta winding configurations trap zero sequence current. I'm pretty sure you've talked about this, but if you have a ground fault on the delta side of a Y winding, you're not going to see any ground fault current. Or at least it'll be extremely low. It should be zero because there's no return path for you to complete the zero sequence circuit. And we'll cover that in more depth. Given kind of these options, really for a two winding, 3-phase power transformer, you can really only have 4 combinations. You can have Y, Y delta, delta Y, or delta delta. And the convention is that the first winding referenced is the high voltage winding, and the second winding referenced is the low voltage winding. So this would be YY, high voltage, low voltage. Y delta would be high voltage, low voltage delta, high voltage Y. Delta Y would be high voltage delta, low voltage Y, and then delta delta, obviously, they're both delta. So I have kind of broken down the voltage and current relationships for each of these 3-phase transformers for the purposes of the diagrams that I did. This kind of defines what the variables mean. So H is the high voltage winding, X is the low voltage winding. That's kind of an industry standard. L refers to either the line voltage, which is phase to phase, or the line current, which is phase current. And that in combination with either H would give you the high voltage line voltage or line current, and with X would be the low voltage winding, line current, or line voltage or phase current. W refers to the winding voltage. So in this case, like your line voltage is a phase to phase voltage, but your actual winding voltage is phase to neutral for a Y connection. So that's what the W is representing. And then N is just the number of turns for the winding. And I ended up making my own graphics for these because, I mean, there are so many examples out there, but I couldn't find one that really demonstrated what I thought was important for you guys to understand without introducing too much confusion. So I ended up drafting these. So I apologize if there's a typo or something in there. Forgive me. I made these myself. So the first winding configuration, 26, okay. The first winding configuration, probably the simplest to understand, is the YY transformer. These are the voltage relationships between the line voltage and the winding voltage. Obviously, the high voltage divided by the low voltage is equal to your turns ratio. And for the line, which is also the square root of 3. I mean, you can separate out the square root of 3 here, but it would also be your winding voltage divided by your high voltage winding voltage divided by your low voltage winding voltage would also be equal to the turns ratio. But I wanted to have that in here so that you could see the relationship between the line voltage and the winding voltage, right? So that the line voltage is the square root of 3 higher than the winding voltage for a Y connected transformer winding. Are you guys understanding this? Like, does that make sense? I mean, you guys have gone through this before, right? This is hopefully review, but
Yes.
I don't
they've
want to
gone through the
confuse
turns
anybody.
ratios. They have got through
Okay.
turns ratios and a little bit of the pacing. Yes.
Okay, all right. I've provided the current relationships as well, and the current relationship between the high voltage winding and the low voltage winding. For a YY transformer, I guess, you know, given that the turns ratio and the voltage ratios and the current ratios of the transformers should be reviewed at this point, what we as protection engineers most often need to understand from a practical standpoint is how the different winding configurations impact our protection. Okay, what differentiates a YY transformer versus a delta Y or a delta delta, and why do we use one versus the other? And so while I provided this background information, which hopefully you already understand, what I want to emphasize for our purposes is what the differences are from a practical standpoint, from a protection engineer standpoint. So for YY transformers, if the neutrals are grounded on both ends, I don't show the ground here, but if they're grounded on both ends, then the YY transformer is a path for zero sequence fault current to flow, right? So you have a ground fault on this side, whatever zero sequence or ground fault current you have on the high side will flow through one neutral into the ground, out of the ground, and into the other one. And you can also, I've never seen this happen, but you can have transformers where the neutrals are tied together, but they're not tied to ground. And that's why in Aspen one-liner, for a YY transformer, you'll see like this configuration, right? It's got this resistor, and this resistor. So you can actually have N be infinity, but 1 and 2 be 0, so that the neutrals are tied, but they're not grounded. And that's why they have that. And like I said, I've never run into that, but just be aware that it could happen. So if the transformers are grounded on both sides, then the YY transformer is a path for zero sequence fault current. If one or the other is not grounded, then it is not a path for zero sequence fault current. So, you know, occasionally you'll see a YY transformer where one side is grounded and the other one isn't. Ground fault current cannot flow through that grounded Y winding, even though it's grounded, because there's no path for the zero sequence current to flow from the high side, because the high side isn't grounded, say.
Andrew,
Go ahead, Blaine.
so quick question, like as you're talking about these different configurations, so are you would these configurations be for a particular or a unique kind of fault that you were looking to protect from?
I guess you're asking, why would you use one versus another?
Yes. Yeah.
Yeah, we're gonna cover that.
Oh, okay. If I'm jumping ahead.
Yeah, you are a little bit, but I guess ask again once we've gone through it, and
Okay.
I'm sure there are other things that are going to come up. There are a lot of answers to that, and the short answer is yes. I mean, there are reasons you choose one or the other, and hopefully we'll cover that during the presentation, during the lectures.
Okay. All right. Yeah. Just curious. Yeah. All right.
Yeah. Yeah. Bring it up again, Blaine, please. Okay. Yeah. If one or the other is ungrounded, there's no path for the fault current to flow through. So that's the key takeaway. That's what you need to understand about YY transformers as far as it relates to like overcurrent protection, differential protection, how it's going to impact your ground fault current on one side or the other. So this is, to your point, Blaine, the YY transformer has two very serious problems. One, if loads on the transformer are unbalanced, then the voltages on the phases of the transformer can become severely unbalanced. And two, if there is a serious problem with third harmonic voltages. If a three-phase set of voltages is applied to a YY transformer, the voltages in any phase will be 120 degrees apart, obviously. However, the third harmonic components of the three-phase voltages will be in phase with each other, since they account for they have 3 cycles for every primary harmonic. So they're all going to be in phase, and that means that they all add up, which is not great. So there is always some third harmonic components in a transformer because of the nonlinearity of the core, and they add up, like I just said. And this can result in very large third harmonic component of the voltage on top of the 60 Hertz fundamental voltage. And this third harmonic voltage can be larger than the fundamental voltage itself, which is not good for the system. So both the unbalanced problem and the third harmonic problem can be solved by one of 2 techniques. Solidly ground the neutrals of the transformer, or especially the high voltage windings neutral. And this connection permits the additive harmonic components to cause a current flow in the neutral instead of building up large voltages. The neutral also provides a return path for any current imbalances in the load. And the other option, which is more common, in my experience, you'll have a YY transformer with a delta tertiary. You can add a tertiary winding, which is a delta, into the transformer bank, and the delta connected winding acts similarly to grounding the Y winding neutrals. That third harmonic can flow in the delta winding, and that tamps it down. So for CMP, for instance, if they have a 115 to 12 kV transformer, they'll do a YY transformer with a delta tertiary, and they don't even actually bring out the tertiary windings. You can't access them. They're embedded in the tank. They're not used for anything except for this issue with third harmonics. It gets rid of that issue. And it also, now that you've added the delta winding and you ground the Y winding neutral on the low side of the transformer, now the transformer actually acts as a ground source, which is really important. That's why they use it for 115 to 12. It's really important for your distribution customers, right? Because you often have unbalanced neutral, unbalanced loads on distribution circuits, and you need a place for that imbalance to flow through. So it'll come out of the neutral in the Y winding, and it'll circulate in the delta. And they'll actually leave the high voltage winding, the 115 kV winding, ungrounded, so that the 115 and 12 kV windings are isolated for ground faults. So if you have a ground fault on the distribution circuit, you don't have ground overcurrent protection or ground differential protection operating on the 115 kV transmission line, because the Y winding on the 115 kV side is not grounded. So there's no path for that zero sequence fault current to flow through the transformer. But you have the source on the low side because of the delta tertiary. So that's kind of an introduction as to some of the considerations as to whether or not you ground the Y side. Do you need a delta tertiary? And that's hopefully what you're gonna, I mean, you're not gonna be master of it at the end of this, but at least understand that there are differences, have a general concept for what they are and why you might use one versus the other, and be able to look it up in the future. You need to know enough to know what you don't know, and to know that you need to go and investigate something, and that you can't just connect a YY transformer in parallel with a delta Y transformer, for example, if that makes sense.
Yeah, it takes a while to get to that point to know what you don't know.
Sure does. And
yeah.
So that's what I'm trying to focus on in this class, is kind of giving you guys the breadth of information and touching on some of the key points so that you're better prepared when you get into the industry to go and look at, you know, particular things, and you can do the homework and the research on your own. You're all smart people, obviously, but just giving you that background information so that you know what questions to ask. That's more than the derivation of every particular equation. That's kind of what I'm focused on. Whether it's right or wrong, I guess you guys will be able to tell me. So looks like we're out of time. Paul's not here. Are there any questions before we wrap up?
I've got a quick question, Andrew. What is a zigzag winding?
I've never actually run into one. It's a zigzag winding it's a way to create a zero sequence source. It's like a grounding bank, but it's not a delta Y connected grounding bank. Let me see if I can find one. So a lot of the training materials that I've been referencing to develop these lectures, like they go through, you know, what happens if you have a zigzag transformer? What happens if you have a 3-winding transformer where you need to connect your differential in parallel between the delta tertiary and the low side Y winding? And those are great examples, but they're all examples of things that I've never actually run into. So I'm trying to tailor it to, again, the practical information. According to the Brave browser summarizer, a zigzag transformer is a special purpose transformer with a zigzag or interconnected star, which is also known as a Y winding connection, such that the output is the vector sum of 2 phases offset by 120 degrees. Contains 6 coils on 3 cores, with the first coil connected contrary-wise, I guess is what it's trying to say, to the second coil on the next core. The second coils are then all tied together to form a neutral, and the phases are connected to the primary coils. But yeah, it for practical purposes, a zigzag transformer, and it's represented like this. It's a zigzag winding. I guess this isn't going to be on the homework, guys. This is kind of what it looks like, and you use that to create a ground reference. Permit the grounding of that neutral to the earth reference point. Yep. So I've never encountered one on an actual project, but you might. Who knows? But that's a zigzag transformer. Any other question, guys? Okay. All right. We'll talk to you guys on Thursday then. Thank you for your time.
Thanks, Andrew.
Appreciate it.
Thank you.
Thank you.
Thanks, Andrew.
Yep. Bye.